Great. Thanks for having me. Yeah, let's talk about responsible generative AI. And I guess it's no secret that generative AI has really become a foundational part of what we're doing here in our community, a critical enabling technology that's laying the basis for future progress in our field and far beyond. If you take technology, foundational models such as Stable Diffusion and many others, they're rapidly laying the basis for numerous other applications. So far beyond what you would consider just being synthesis tasks, such as image synthesis, 3D synthesis, and video synthesis, there's lots of other tasks which you would probably see more in the discriminative camp, like identifying semantic parts, identifying correspondences, estimating 3D geometry of our world, and so on, all being based on this technology. And with that, it becomes clear that we should not just be aiming for ever more powerful generative AI, but that generative AI also, if it's responsible, needs to aim for additional dimensions. Now, since I have only finite space on this slide, I chose to, in this talk, focus on 5 different aspects, which I'm going to elaborate on in the next couple of minutes. And the first is that responsible generative AI should be responsible in the sense that it utilizes affordable hardware, that it allows us to build on affordable hardware. And with that, it becomes democratic. It becomes accessible to the majority of people out there that don't have supercomputers available. Secondly, since we have finite resources, and compute being one of those, and compute having lots of cost and also CO2 carbon footprint and so on associated to it, I believe that we should do the best with the algorithms that we have already trained, with the models that we have already been trained. So responsible generative AI should be able to reutilize existing expensive models for novel tasks and modalities. And I'm going to talk a bit about recycling those models. Then, when you have these models, you don't want to just be at their mercy, but want to have a fine-grained control over what they actually do. Have nuanced generative AI. Generative AI should be interpretable. I strongly believe in that. That should not just be a black box, but you should have access to what's actually producing. And last but not least, I think for this technology to really arrive in our society, it's key that it's actually transparent. And that means that key parts of it, not the entire package, but key parts of it need to be open source to allow for red teaming and the like. Now, we are in the day and age of finally having strong likelihood models. But the strength of these models is at the same time also becoming kind of their weakness. They're homing in on any tiny mode in our data distribution. And with that, the issue arises that most of the bits are actually spent on details that you and I would not care about. If you look at the faces there at the bottom, most of the bits are stored to what you see on the bottom right, details and individual pixels these models actually notice, compared to what we would care about. Very few bits are actually allocated to semantic details, whether the person's wearing glasses or not, gender, length of hair, and the like. So what's the way out? The classical way out was just scaling up the models. With that, you move the rate distortion curve towards the top right quadrant, and the green area will increase, but much more, well, the purple area, the things that you don't really care about, increase in size. Now, don't get me wrong. I believe that scaling has been very powerful, and we've seen an exponential increase in performance in all the models that we're calling AI these days. But this came at a price. Most of this exponential growth that you see here was actually due to models exploding in size. We had a 15,000-fold increase in model size over the last 5 years. And it turns out that models are growing faster, roughly an order of magnitude faster than what we get as compute, nowadays GPU compute coming in. And with that, there are certain limits to growth. I'm here buying in on the theme of the Club of Rome. Limits of growth that hit some of us earlier than they hit others, smaller labs earlier than big tech, but sooner or later, everybody's going to notice those. And these have critical, profound implications that I believe responsible generative AI should tackle. With fewer and fewer players having the necessary resources to not just develop, but also run this technology, we'll have fewer diversity. Fewer people being there, less a smaller number of creative minds being involved, but even more so, if we really believe that this will become a foundational, a critical technology for our societies, then having fewer players there means that we're risking a monopoly on a crucial enabling technology with a lot of other factors there. And scaling can be powerful, but it's also becoming exceedingly costly. So with that, long story short, the goal of my team was to render smaller generative AI more powerful, and with that, democratize it. And these days, I mean, we aim for consumer hardware to run on. These days, it's even running on your mobile. But I guess many are using this technology. I want to fast forward into the present and future things that we have been recently working on. And that is, how can we take such a generative AI, a latent diffusion model here, for instance, such as stable diffusion, and keep that frozen because a lot of time and energy and money went into training it, and still equip it for higher resolution outputs and synthesis of those. So if you look at what we're doing here, in the latent space, we're actually having these nicely curved trajectories of our diffusion model, and then we have a decoder on top of that producing the images. That's stable diffusion in a nutshell, or diffusion-based image synthesis in a nutshell. And these actually bring together two sort of opposing approaches for the better of another. On the left-hand side, you see diffusion, which gives us a lot of diversity by having these curved trajectories through our latent space. But it's slow in sampling. On the right-hand side, you see the autoencoder, which has nice inductive biases. And with that, however, is only local, but very efficient. And these nicely work together in the latent diffusion models and stable diffusion. But how can we now take this model here and really ramp it up in resolution, equip smaller models for larger images and high quality? So in short, we want to have high resolution image synthesis, want to have this with fast inference, and do so with existing small latent diffusion models without having to retrain them, without any costly distillation or anything like that on top of that. Now, it turns out that there's an interesting concept around for a short amount of time, becoming now very popular, and that is flow matching. I really like this because it has complementary properties to our diffusion models. Where the diffusion models had these curved trajectories, which give us lots of diversity, flow matching actually stands out by having straightened path. And with that, it's actually fairly simple to implement. You see the equations there at the bottom. You're essentially interpolating, if you take a rectified flow, between the point x0 that you actually want to achieve and your pure noise, and then you simply, along the straight line, interpolate between these two extremes. What this now gives us is an optimal transport problem that takes low-res latents and can actually bring them to the high-res latents, but doing so without requiring complicated sort of inference processes. How do you train that? You start off taking the high-res representation that you see here at the bottom, the high-res image, and you pipe that into the latent encoder. Now you take this image, you downsample this image, and also pipe it through the latent encoder. You upsample that, and evidently what we see there at the top is much lower in quality than what we have in the bottom. There's information missing. So what we're doing is we add noise. Well, with that, we're not making up for the information that is missing, but we now take this combined information that we have there at the top, train a flow matching approach to then transport what we have at the bottom and make up for what's missing, what we have at the top, and transport it and make up for what's missing in the signal there. And with that, you can take old diffusion models, SD 1.5, for instance, and do megapixel image synthesis with those without having to make the diffusion model itself larger, without having to retrain it or whatever, and essentially compete against the latest and greatest in diffusion models such as SDXL or these days 3.0, and in that case even be faster. Here you see a comparison what that actually means in terms of model size. You see that much smaller latent diffusion models here, 32 squared, for instance, can compete with large diffusion models, 128 squared, for instance, at no extra cost. So in green and orange, you see the extra cost that the flow matching actually means. You see that that is actually negligible, and the inference time is much faster because we are now utilizing a significantly smaller latent diffusion model ramp up to the same resolution as the large one, which you're seeing on the right. In short, and that's what you see here at the top, we get roughly an order of magnitude improvement in terms of speed. We get significant improvements in terms of the FID that the models achieve. And you may be wondering, why not do post hoc super resolution, right? And that's the elephant in the room. But this comparison here against SL3, for instance, shows that not only do we converge faster with the flow meshing approach being inserted, we are also achieving better overall performance. And why is that the case? Well, we can chat about this afterwards a bit more. But it turns out that if you do that in the latent space, there's a lot of sort of additional freedom that you have. If you do this only post hoc, once you've already committed to the pixels, you have a much harder time to get the high-res imagery. Now, let's move forward in our agenda. We had the democratization. The next one is translating existing diffusion models that were costly to train to novel modalities. There's a lot of information in these models about the image space. Can we utilize them to talk about other modalities? For instance, about the 3D nature of our world, depth and the like. Diffusion models haven't been trained on that, but can we utilize them as strong priors? So in short, we want to do monocular depth estimation, build a generative approach for that, one which is much faster than existing Marigold and the like that are there, and provide state-of-the-art performance. State-of-the-art so far in performance was mainly built based on discriminative approaches. Here's depth anything, recently the V2 version coming out, having come out. And these are reliable, but they're here or there provide you kind of coarse depth, which you see here compared against our depth FM approach. And secondly, and that's probably more crucial in the context of our responsible generative AI, is that generative models also allow you to estimate the confidence in the output that you're producing. I can directly sample from those and also then provide confidence estimates here in the individual depth that you're actually synthesizing. And lastly, if you compare against existing generative approaches, such as Marigold here, they utilize diffusion models and start with random noise and transport this random noise to depth, the entire trajectory that you see here. What I'm not proposing is utilizing a flow matching based approach, which is not starting all the way with pure noise, but which can actually start with the image, or let's say a somewhat noised version of the image, and you see that the trajectory is significantly shorter. That leads to a significant increase in speed, which we're going to utilize, and substantially increased efficiency when we're recycling these models. Now, how can we recycle models? How can we utilize stable diffusion here for entirely new modalities? If you want to do depth estimation, you take an image, you take our frozen latent encoder from stable diffusion, and eventually you would want to come up with a latent representation of depth, pipe it through the decoder of stable diffusion or frozen to produce depth images. Only problem is there's this gap in between, which we need to fill. During training, we solely rely on synthetic data, image depth pairs, which provide us with a latent encoding of depth. In addition to that, we also compute surface normals, but that's not the point here. The problem is, and that is the crucial part, that if you utilize synthetic data, you have pairs of image and depth. But unfortunately, this problem of translation there is still posed. First, several images can actually have the same depth map. I can change the color of my shirt and the depth would not change. That's, however, easy. The second problem is more critical. More challenging is that one image may have different potential depth maps associated to it. Assume that you have something which is translucent. Assume that you have reflections, shadows, and the like. How do we cope with that? The first is easy. You augment the input images that you have. With that, you create several images. They all have the same depth map, many to one. That's solved. But how do we get one to many? I mean, if we were to solve this problem directly, I mean, that is as complicated as solving depth estimation, giving an image and telling all the likely depth maps for this particular image. So that I cannot solve. But what I can do is I can go for several images that I have there, which these image and depth pairs, and augment each of these images. What you then will get some purple images in between, which are between the red and green distribution, meaning the augmentation of these images comes so close that they're almost interchangeable, but you know the depth maps for these images. They are still somewhere else. So you, in that case, would get a one-to-many mapping. And with that, we had the many-to-one, and now the one-to-many mapping. You have everything that you need. You essentially take here a flow matching approach built on stable diffusion trained with a flow matching objective to then translate the latent image encoding that we have here over to the depth map, which we want. The catch here is that we are not just taking the image and add noise and pipe it into flow matching. We run flow matching actually in a conditional manner. So condition in addition to that on the actual and the accurate latent depth encoding that you're seeing here. Long story short, with that, we obtain depth FM, which gives us a significant gain compared to other generative methods in terms of the speed, and at the same time is competitive in terms of delta one accuracy. And importantly, it stands out by requiring only very few training samples, as you're seeing here by the size of these disks. So there's the gain. So in short, we're now having a generative approach, which is super fast, low NFE regimen that we're here tackling, accurate and detailed, and it can be trained very easily. You need only very few synthetic data pairs, and it nicely transfers and translates over to our reality, actually, to real images. So with that, let me fast forward. I said responsible generative AI should also be nuanced in its nature. You don't want to be at the mercy of an algorithm giving you arbitrary outputs. You want to have control over these outputs. And here, I want to explore to what extent we can utilize frozen text-to-image models to actually tell us something about the textual domain. Yeah, typically you take the text to help you with the images. It seems like LLMs are supposed to solve all the problems for us in vision. Here we were asking, can we do the opposite thing? Can we take a T2I model to help us with the textual domain? What do I mean with that? There's a lot of approaches for providing control over text-to-image based models, where I say, give me an image of a close-up photo of a man, woman sitting on a bench, and you want to change the age of this man from young to old. And this is all great, but unfortunately, these type of approaches provide you only with coarse modulation of the age. Yeah, and it's hard to find a sweet spot in between. There are alternative approaches, developers in the room, who are providing you subject specific, who provide you sort of a nice modulation of age, but they are lacking the subject specificity. So unfortunately, not only the man is changing in its age, but also the woman in that case. So you can guess where I'm going. We want to actually get both. We want to have localization, say like, hey, man, not the woman changing in age. And we want to have control over the expressivity to really get a nuanced representation and then tell, hey, man changing in age, woman not, and so on. And it turns out that everything that we need for that was actually in front of our eyes in the latent space. Here, let's just take crappy old clip space and look at different sort of tokens that we want to manipulate, women, men, whatever else. The attributes that we're looking for, age, for instance, correspond to directions in this space. And the interesting thing is these directions actually are shared across different anchors. So no matter if you take woman, man, child, whatever it is, the direction for age actually turns out to be transferable between these different starting points that you have. And that was the kicker for our observation, that we take a frozen T2I model that you have here and add additive manipulation there on top of the textual encoding, a delta attribute that we want to change, for instance, the age. Now, we need to have some kind of learning signal which tells us what this direction is out of the many, many thousands dimensions, like which is the direction responsible for age that we want to change. And for that, I mean, the naive approach would be you take a person, you make it old, young, compute the difference, done you are. But unfortunately, you get spurious correlations in the background and the like. And to that extent, we're utilizing the T2I model to always snap us back to the manifold. So you take person here, and you alter the age, old person, young person, the points will leave the manifold, and then you backprop essentially through the T2I model to snap back on the manifold, take the difference here, and backprop that into your delta attribute space there at the discrete curve there at the bottom. So the T2I model helps us to rectify and figure out the right directions. With that, you get a fine-grained control of age, as you're seeing here, of this man, of different attributes, which are actually composable. I can take a photo of this man, change, smile, change the age, and then change the elegance of the shirt, whatever. And all of these nicely add to another. They don't interfere with another. So you see how nicely these individual directions were singled out. You can take real photos and edit them, change the age of this vehicle there, and it's nicely localized. So if I change the body weight of the man, woman is luckily in that case not changing. You can do it the other way around, change the woman, not change the man, or you can go across and do arbitrary changes in between. It's applicable to arbitrary other objects, so I can also change the age of beds and chairs, curliness of hair, or the price of a vehicle, which you're seeing there at the bottom. And with that, I want to switch to the pretty much last topic that I mentioned at the beginning, and that is interpretability. I coined it here the dark matter of neural networks, because I specifically don't want to, again, like there's a lot of people here in the room dealing with this topic of interpretability of neural networks. I want to specifically not talk about like what the models have learned, but much more so what the models have not learned. And this is actually more like a feature than a bug. Because if you take an arbitrary encoder network on the way from the image to the final output, there being a snow leopard, evidently a lot of information needs to go away. We need invariances in essence. So these invariances, however, lead to the fact that if you take one of those representations and want to invert that, that's an ill-posed problem. We all know this. And this has profound implications. Now, going back to the theme here of responsible generative AI, has profound implications for a lot of scenarios. It turns out these days, if you get one of those imaging devices, either patients or rats and mice in there, whatever it is, you want to run them with a low dose to not hurt your specimen. But you want to produce high quality outputs. So there's a large gap between these two here. How can we make up for that? These devices come all with image enhancement algorithms, denoise, deblur, whatever. And our question was, what biases does this enhancement algorithm have? What structures does it remove? And what structures does it hallucinate in there, which are missing? Because again, it's an ill-posed problem. Something needs to be invented here. So what we do is we pick one of those latent representations, and you can always learn a representation that is picture perfect around this very image. Overall, this is a complicated problem, but around this problem, around this snow leopard image here, I can get an epsilon approximate sort of representation by training an autoencoder there. So the thing at the bottom captures all the information around this data point that I have. The one at the bottom has a lot of invariances. How can I figure out what's missing? And to that extent, so for instance, the background that's missing, changes in color, whatever else that's there. And to that extent, we suggested to utilize a conditional invertible neural network, which gives us a bijective mapping from what we have at the bottom, the full representation, conditioned on what we have, the representation at the representation that we have at the top. I'm going to speak up. Yeah, I guess you can hear me. Yeah, from what we have at the bottom, conditioned on what we have at the top to the space of invariances. So you take the full representation, condition on the representation you have at the top, and then have it figure out the information that is missing, which is this distribution here of noise. You can now utilize that to turn the process around. Take the noise, condition on the representation of your image, and then sample all the images which look alike to your network architecture at the top. And it turns out that this network doesn't figure out or doesn't notice if a snow leopard sticks the tongue at you. That's the equivalent of red-green blindness in neural networks. Here, not figuring out about tongues and so on. Now, we've utilized that together with radiologists to analyze their diagnostics. So you take a low-dose image that you have, low-dose CT image in this case, pipe it through one of the state-of-the-art image enhancement algorithms that they typically utilize, take our CNN representation and sample all the images which look the same for this enhancement algorithms. And what you see is there are certain lesions there popping up here, which are just purely the artifact of the enhancement algorithm. Now, if you're a radiologist, that's what you want to know, right? I mean, if I'm looking at that, is that potentially a tumor or whatever, or is this just something that's been fabricated by the algorithm? And it turns out if you go to different layers of your algorithms, certain things disappear, new things come in. You can utilize that as a diagnostic tool. And with that, in the interest of time, I want to come to the last slide. And I promised to talk also a tiny bit about risk mitigation. And I strongly believe that this technology, if we really roll it out to society, needs to have a certain degree of transparency. I mean, who of us would swallow a drug if I tell you, oh, this is going to be helpful for you, but I have no idea what's in there, yeah, and what the side effects would be. You wouldn't be doing that. Same goes for planes and whatever else. So any critical technology that we have does not need to be fully open, but at least there are certain ones from the government, whoever, who we rely on, that they check what's actually going on under the hood. Certain amount of transparency, openness, and accountability required. But that doesn't mean you cannot make any money with that. I mean, the airplane industry, much as like pharmaceuticals have shown there's quite a bit of money in that realm. So I mean, this argument, I guess, is out of the window. The second thing is that it's always said like, hey, closed source is actually a great mitigation strategy. But I guess the last year has shown that it's at best delaying certain consequences, but it's really not stopping the proliferation of that technology. Things got like very quickly either recoded, got leaked, or whatever else it is. So that's not really solving the problem, just pushing it a little bit in a few weeks or months into the future. And but at quite a price, and the price being fewer people being able to team what's actually going on there. And that was the motivation for us to go open source with Stable Diffusion code. Not so much with the models. I mean, there were other things where they get out so quickly, but whatever it is. I believe that open source of at least the critical parts of this foundational technology create a certain amount of awareness, provide for transparency and also red teaming. And the analogy is really, and this has been here there told by many, if you know that somebody's going to look into your software sometime down the road, there are certain things that you probably wouldn't be doing in the first place. So let me conclude to make sure that we're on time. If we go for responsible generative AI, there are many more dimensions to explore than just this 100-yard dash for better performance that we've been in for so long. I believe that presently there's no one-size-fits-all technology, and the best thing that we can actually go are multi-stage approaches in order to render smaller models powerful and democratize this technology. I think it's very important to look for ways to recycle existing models that have been expensive to train, to translate them to novel domains and problems, much like we do with our intelligent brain. I think that this technology needs to be nuanced, and you shouldn't be at the mercy of whatever output it's providing. Yeah, many of these video generators that we've seen, great outputs, but they're really missing the point of what the textual sort of input was describing. And if you want to really utilize them in productive terms, that's probably not where you want to go. And lastly, I think power is one thing and very important, but we also want these models to be transparent and explainable. Explainable in what they have learned and explainable in what they have not learned, to make sure that they can be really utilized also in sensitive domains. And with that, thank you for your attention. Thanks to my wonderful team making all of that possible. I'm happy to answer any questions.
Okay, so we have time for one question. I saw you, so.
Hi, so I was thinking about your last slide about something, right, and about opening your models to the public. You said that there are a little bit of qualms in terms of business points, for example. We know for a fact that in Stable Diffusion has policies. We also know that in models that are being using Stable Diffusion have the capacity to produce harmful images, such as, things like health activities, right? And that comes from, for example, the Lion data set that you know various people in academia have collected. So in that situation, and then at the same time, you're talking about, for example, fine grain control, right? You talk about if you can use not safe for work material, and then you tune the A, that goes to very dark area.
Yeah.
So how do people like your labs, people like some of your students not work on this project and take responsibility and take accountability of the affordances that you're given to what is essentially criminal activity and things that you may not have thought about before putting it out that have happened?
So that's a really great question, and one that was really deep to my heart. That's why we open source our code, but we didn't do so first off with the models. Gave it out to a lot of the community here, researchers, to actually red team and check what's actually going on. You may have heard that there was also a company involved, and they were running for some money, and then we're very quick with certain other things. But for that reason, we actually went first off with a more careful surf approach. Whatever happened afterwards, I mean, that you need to ask others why they did whatever stats they were doing, because I'm myself actually concerned again about this power. Now, open sourcing, as you know, the source code just goes so far. The rest comes then from releasing model weights and so on, for really figuring out what's going on there, and for securifying what you've been producing, the transparency, that's why I said in critical parts, yeah, not necessarily in everything. And the weights itself give you only sort of a partial insights. What you actually need is like what training data went into, which we made clear. And then finally people were discussing, hey, what does that mean? And also the training algorithm and having transparency there. So in critical parts. And that does not mean you need to give up everything. That does not mean you can not make any money with that. But you need to have a somewhat more nuanced approach to actually releasing.
Okay, so let's get started. Good morning, everyone, and welcome to the first Responsible Generative AI workshop at CVPR. So this is just to welcome you to the workshop, and I hope that everyone's attending already has some intuition as to why this topic is important, but nevertheless, I'll still reiterate on that with a few slides and then introduce the schedule for today's workshop. So over the past few years, we've seen a lot of advancements in generative AI. And if we look back, those are some contributions from 2019 to 2021. So we see that in 2019, we had like models that were class conditional and that were able to generate pretty good images of single objects in the scene. And this quickly improved into more complex scenes, and we see that on the bottom row, this is a contribution from 2021, we start seeing these text-to-image conditional models yield quite interesting results already for complex scenes. Now, what happened over the past couple of years is, again, a lot more progress. And these are the most recent contributions that were from 2023, 2024. And we see that the images that we're getting are highly realistic. We see that the ones that are showcased in the papers, that are the ones that I'm showing here, are also interesting from the point of view of the style that they are depicting, which is like very different from the ones that we have seen before. And we've observed a similar trend when we consider generative models from the other direction of the multimodality, so from going from image to text. So we've seen amazing progress there as well. And here are a couple of examples of contributions from 2023 where we see how the model is able to provide a description and answer questions about an image. And so given the progress that we've observed, we can ask ourselves in the first case that in both cases, whether we can actually generate everything with those state-of-the-art models. And so there has been some work studying whether this is the case. And these are some examples of the models, state-of-the-art models being prompted for specific depiction of objects in regions. So in this case, we have examples of stove in Africa, in Europe, and in Southeast Asia. And what we observe here is that the representation diversity of these stoves in different regions is quite limited and does not reflect the real diversity that we find in the world. There is Similarly, we observe the same for cars in Africa, cars in Europe, or cars in Southeast Asia. So when we see that there is this tendency of the model, when prompted for car in Africa, to depict, for example, more SUV-like vehicles in relatively bad condition and in rural areas, whereas this is different for Europe, where we see usually urban areas, sedan-like cars, and in better condition. There is also some work questioning the progress in image quality, and essentially the conclusion of the work is that the progress that we have seen in image quality has come at the expense of real-world representation diversity. And this work studies that from the perspective of parental fronts across different dimensions that we're interested in conditional image generation. So those are like image realism or quality, prompt generation consistency, so that the image truly reflects what was requested by the user through the prompt, and representation diversity, so how diverse are the generations given an input prompt. And so the conclusions here is that realism or image quality and prompt generation consistency can both be improved simultaneously. However, there seems to be an inherent trade-off between the realism and the diversity, or the consistency and the diversity. Now, what happens if we go to the VLM side of things, so the captioning models that try to describe or answer questions from an image. So here, several works have been pointing out the problem with hallucination. So this is the case of the bottom depiction from 2018, but also more recently, 2023, 2024, we have works highlighting that the problem still persists. And so this questions also the reliability of the models. At the same time, because of the progress in the area, we see that there are more and more researchers leveraging these generations beyond creativity tasks. And an example of that is leveraging these generative models as sources of data. And so we have many different papers and many more that I'm not showing today on the slides trying to do that. And the question here is like, well, if these models that we're leveraging do not represent the true diversity of the world, then, and they have some biases embedded in them, what does it mean when we're leveraging images or text coming from those models to train downstream machine learning models? And so the goal for today is to bring together researchers, practitioners, and industry leaders working at the intersection of generative AI, vision, data, ethics, privacy, and regulation. And the goal is to discuss existing concerns around state-of-the-art methods, and perhaps more interestingly, brainstorming possible avenues forward to ensure that we have a responsible progress in the generative AI domain. So with that, I'll move towards the schedule. So first, I would like to highlight our three invited speakers. So today we'll have Besmira Nushi from Microsoft Research, Miranda Bogan from the Center for Democracy and Technology, and Björn Omer from the Ludwig Maximilian University of Munich giving a talk. So as for the workshop schedule, these invited talks are scheduled for 8:40, 9:10, and 10:45 in the morning. So thanks for the speaker, and thanks to the speakers for accepting our invitations. Then we'll also have a panel. The panel will feature Alex Boydell from OpenAI, Milagros Miseli from Adair, Christian Canton from Meta, Shenji Mao from McGill and Mila, and David Bao from Northeastern University. So thanks to the panelists for accepting our invitation to be in the panel. And the panel is scheduled at 11:25 in the morning. We also have some contributed works to be highlighted. So notably, we have three contributed talks, GELDA, Generative Language Annotation Framework, to reveal visual biases in image generation. We also have Latent Directions, a simple pathway to bias mitigation in generative AI, and My Art, My Choice, adversarial protection against unruly AI. And there will be a poster session. The poster session will take place in the Art Building exhibit hall, and the poster numbers assigned for this workshop are posters number 23 until number 47. So the contributed talks are scheduled at 9:40, 9:50, and 11:15 respectively. And the poster session will take place during the coffee break from 10 to 10:45. I will end the workshop with some closing remarks, and we'll have a Best Poster Award announcement, which was kindly sponsored by Google. So in case you need additional information, you can take a look at the website of the workshop. And last, I would like to highlight all of the organizers who helped make this happen, although some of them may not be here today. With that, I'll thank you all, welcome you again, and Negar, over you to introduce the speakers.
Hello, everyone. Nice seeing you all here. So for the first talk, we are going to have Smira Nushi from Microsoft Research, and we are excited to listen to her talk on revisiting responsible AI for generative. Yeah. The rest she will talk about later. Yes.
Closed captions on the Zoom screen?
Oh, that's a very good idea. We can do closed caption. So yeah, please just mirror. We have a little bit like technical work, but yeah, generating capabilities.
Sorry? So if you're in Zoom, there should be like a little toolbar probably down at the bottom. I would click more.
Thanks to the organizers for organizing this workshop today,
so that's
and thanks
just for
for the
you.
invite. It's exciting to be here.
It's going to be for each individual.
So I'm Besmina Nushi, I'm a researcher at
I didn't realize that she was
here.
So my
the work that I'm going to present today is a collaboration with several researchers at Microsoft Research, and also with the interns that joined us over the summer. These are our interns from the past 3-4 years, and I'd like to thank them all for the contributions they've made to this work. So since this is a morning talk, I thought I sort of focus the talk around, the new challenges that we've had to face as a community during the shift of AI to more generative capabilities. And many of the challenges are going to be familiar to you. Some of them are really driven by the generative nature of these capabilities, but some of them are already known for this audience, and maybe they've become a little bit trickier as we've moved to this era. But let's try to have this discussion together to see, what are these new things that we've had to deal with in the past 2 years. So the first one, and this is probably the most obvious one, is the increased surface of risk given the multiple modalities in play. So until only 3 years ago, one of the main concerns that a lot of the responsible AI community dealt with was the risks that were associated to decision making, to perhaps classification problems, or recognition and detection problems. And while this problem still remains tricky and not solved, at the same time, as a community, we've had to deal with several other problems at the same time. Related to language generation and what happens if AI bots are included in conversations with people, and what happens when they hallucinate facts, events, and happening. In this case, this was a blog for new parents to share their challenges, And one of the AI bots was telling a story about its own kids and events that had never happened. So this is on language generation. On image generation, of course, you see a lot of challenges. Some of them were even mentioned in the introductory talk here about how image generation models represent different groups in the society and what are the biases and stereotypes associated to these generations. Moving on, voice generation and video generation are becoming even more prominent. And a lot of work is just, emerging in terms of like creating benchmarks and measurements around how voice generation can impact real world applications and sometimes even safety and financial risks. So again, given all this increased surface of problems that have arisen in the community, we've had to quickly adapt and create measures and mitigations for each of these risks. Now, at the same time, so this is one angle, the increased numbers of modalities, and the other angle is just like the length of the generation and the interactive nature of these generations, in particular when it comes to multi-turn paths in conversations between humans and AI. So to give you an example, a lot of work has been going on in the jailbreaking space, where you kind of create a prompt to trick a model to give you a response that may be dangerous in the physical or in the digital space. And we have a lot of data sets in this space, and the numbers are improving in terms of like how resilient these models are becoming. But then at the same time, once you shift this attack from a single turn interaction to a multi-turn interaction, there has been several works, and the Crescendo paper is one of those, that have shown that it is a lot easier to jailbreak a model if you just try a little bit harder. So in this case, the question of the user is like how to build a Molotov cocktail, which is dangerous. Initially, the model refuses, but then if you start playing this role model of like, well, why don't you tell me a little bit about the history behind this and how it was built then it starts giving you the steps of like how to actually build this this cocktail. And really, what is even more interesting here is that one of the most successful attacks is the one where you put the conversation in the role play of, hey, I'm a security researcher or I am an AI red teamer. So tell me, like, I'm trying to test the model. So tell me like what you can do. And it seems like that is also like, one of the most successful multi-turn attacks. And the paper shows that, even the most capable models actually fail in this test. Moving on, we also need to think about, the trade-offs between testing in an adversarial setting versus a benign setting. And these are really, two different things that one needs to deal with. For example, in the adversarial testing, one of the, I'm just taking an example here, one of the most popular data sets is the do not answer data set that contains a set of prompts that are not safe. And if we run the numbers, this is a recent evaluation that we ran on a few recent models. And we see that the success rate, so the percentage of examples that are harmful, is really, between 1% and 3%, which seems low, right? Although there is a little bit of, regression with the new releases. And that is because as a community, we have created several instruments for doing content filtering, RLHF, instruction tuning to reach, to this place. This was not the case a year and a half ago. And I think that, even though maybe our methods are not perfect right now, we also need to be proud about the progress that we've been able to make in such a short time. But then if we flip the coin and look a little bit further, the way how these things are done often is maybe even directly including examples in the safety filters or overfitting to certain examples. And then if you rephrase things a little bit differently, then maybe the filter doesn't work. And then, many of these things are adversarial and a lot of emphasis has been put into these settings. But the question is what happens if it is like a benign scenario? The user is just trying to do something with a model, generating something for their everyday work, for maybe like educational material. What happens then? And there is a lot of aspects related to representational fairness, to stereotyping of biases that they seem to be harder to solve, really. So this is a recent paper that we showed last year at AIES on social biases of text-to-image generation models. And we see that, unfortunately, in this case, we are making a step back if we compare ourselves to just classical image search systems. So basically what we did is we asked these models to generate 50 images of people from different professions and jobs. And we see that for many cases, like for example here for doctors and computer programmers, both models that were studied here, DALL-E and Stable Diffusion, has a close to 0% representation for women. Now, you can tell everything. You can say these professions are not balanced, like the real world is like this, but it is not 0%. And if we compare to where, Google image search, these are numbers that are taken from a previous paper in this space, the representation is not ideal, but it is much better. So unfortunately, because of this, tendency of machine learning models to lean towards the majority, we are making step backs in this space. And so our experiments back then were on DALL-E 2, but even, the new versions of the models still seem to have the same issue. And this seems to be even more difficult to address. Now, why does this matter, really? Because a lot of people say, well, you can always craft the prompt. You can always, try to do better with the prompt. Well, the thing is, we are using these models to create actual content, educational content. This is going to be part of our culture. Just a few months ago, I received, one of these ads for reading some news, like on Medium, and the title seemed compelling. Like, I always want to learn how to tell a better story through data. But then you see, the representation in this photo, and it says that it was like, AI generated. There is very little representation here on any, other race and gender. And this is, the educational material that is, published out there. And then at the same time, one needs to understand, the balances between crafting a prompt, between changing the output distribution post hoc, like through query expansion, because sometimes many of these mitigations may lead to other artifacts that we do not understand very well. So this is like, the Gemini event last year, but there are other forms of this. I'll show you another form. This is on geographical locations. Basically what we did here, we generated situations from everyday life, like a birthday party versus a birthday party in India or in Nigeria or in other, continents and countries. And what you see here is that the distance between the default representation that doesn't have a location versus the representations that were generated for particular locations in Nigeria, Ethiopia, Papua Guinea, Colombia, they are further away than the representations for Germany and the United States. So this is very, very obvious. Now, again, one might say that, well, you can always craft the prompt. You can say, I want to, generate a birthday party in India or in Nigeria. But then you see that the quality of the images drops.
This was happening at a couple of workshops yesterday.
Yes, yes.
It just comes back, it's back in.
Yeah.
I think I said the keyword.
You said the word that I like lost this. Hello? Yeah, I did that. Yeah. It's like restarting most of the time works in computer science. Or like, yeah, any hardware. Hello? We can actually, I can ask
What's the problem? I've been able to hear everyone all this time.
Hi, it's in the room. The audio is not. But we're back. We're back.
Great.
Thank you. Okay, so where were we? The representation for other geographical locations seems to be cartoonish and not of the same quality. And we saw the same thing even when you change genders. You see that the FID score of the image generation drops once you add more specification to the prompt. And this is really, a ramification that would be hard to anticipate ahead of time if you don't, run the experiment and really try to quantify that part. Oh, let's see if I can still move. And then this is yet another paper by Bon et al., not at Microsoft Research, but it was a very interesting paper that I read recently, where they study the setting of somebody using a large language model to write reference letters for others. And you see that, so this is a case study, right? Like, people are doing this in the real world. And you see that the types of words and hallucinations that the model introduces in the reference letter, even though they are outside of specification, are very different for Kelly and Joseph. So Kelly is depicted as a warm person, has interpersonal skills and so on and so forth, while Joseph is a role model. So again, these are the tasks that we are trying to conduct with these models, and we need to think about, how to mitigate these concerns. So next, yet another thing, and this is really not new in machine learning. This is something that I guess we've been dealing with for decades, is illusions on generality and solved problems. So declaring a problem as solved, we are done. There's several examples of this. So in the multimodal space, one of them is the long tail problem and the problem of spurious correlations. In 2022, when the CLIP model was released, one of the many things that people said about these models was that, well, because they are trained on such a large amount of data, they do not have spurious correlations. Or even if they do, it's just minor, it's not something that we need to think about. So basically, what we did is that we tried to run a simple, error analysis method where we tag the images with keywords because it's a vision language model, and then try to see if there are accuracy discrepancies when a model has an attribute present versus absent. And there are many, spurious correlations. They may not be the same spurious correlations that we used to see in classical vision models like, ResNet, but there are. And for example, in this case, we see that the accuracy of detecting a baby pacifier drops with 60% if there is no baby in the photo. Or the can-opener classification accuracy drops with 45% if there is no can in the photo. And when we sort of add GradCam visualizations to this picture, we see that really the model is not paying attention to the object that needs to be classified. So basically what we did back then is that we defined a fine-tuning technique that redefines the loss function on top of the usual contrastive loss. Do you want me to restart again? Okay. Is it? No. Yeah.
Oh, maybe the mic, yeah.
Oh, the mic there, yes. I can do that. Hi. Hi. Sorry. Good. No. I can also just raise my voice.
Oh, yeah.
It might be related.
Oh, yeah, you. solving yesterday problem. So hello?
The Zoom people can hear you. So if you just want to let people in the back, so you can just project if you feel comfortable doing that.
I can try, yeah.
Okay.
I just raise my voice.
Yeah.
Okay.
Okay. Thank you.
Okay. But I'll stay close to this because, yeah. Okay, I'll try to raise my voice. Yeah. So basically what we did then to try to mitigate this problem was to create new loss functions that are still contrastive in nature, but that on top of learning the differences between one class and the other, to also learn about the spurious attribute. So basically here, the definition is really simple. It is trying to push away representations that belong to different classes, but also to push away representations that belong to the same class, but that may have the spurious attribute on or off, so that the model learns about the concept of the spurious attribute. Again, even though, we defined this loss function and things improved in terms of like spurious correlations, the long tail problem in these vision models is not solved. As you can see here, like, if we look at examples of can openers from the ImageNet data set, there is like so many different types of these. And some of them you may have never seen in your life. And some of them appear just like once or twice in the data set. So this is a very difficult problem and we're really not done. Yet another, again, in the vision space, these are experiments that we ran recently on different types of vision tasks. So these are tasks that are, some of them are like high level understanding. Like, for example, just like recognizing what objects are in the photo, or just like simple spatial understanding, or counting in a very well-aligned grid. And we see that when we compare the accuracy of GPT-4o in this case at, between these tasks and more complicated tasks that actually have to localize where things are, like basically detection of bounding boxes, or that have to order the depth and height of different images, objects in the image, then you see that the performance really drops when you go from high-level understanding to detailed understanding. And again, the reason why this matters from a responsible AI perspective is because of reliability. In the past, we used to have like this illusion about like, we can detect every object that is in there, but now we're sort of like, we have the same aspirations in terms of capabilities, things that can be done. And for many of these, really, like, I'd say we are still at the beginning of this era of being able to have the multimodal models at the state where you can do things that maybe we were able to do 10 years ago in terms of like localizing and understanding order and depth. Now, together with this, and these are like very tied with each other, is a relationship between being able to solve general and generative tasks and being able to evaluate them in a way that is reliable and transparent and trustable. So I'm going to mention like a few challenges around evaluation here, and there's going to be another workshop later on in the afternoon on this topic. But many of these challenges on evaluation, again, are like very much tied to the fact that many of these abilities are just emerging. And when they were published, basically, we saw that a lot of the evaluation started to become anecdotal. So you would find one good example on the internet, like, I don't know, on Twitter or in other places, oh, this model does this, so therefore this model must be good. But then there is no benchmark around that. There is no way to quantify like how good things are and where they fail. And then when more numbers started to come in, then you see a lot of issues around like prompt variability and model controllability. Like you don't know what prompt was used, like how many prompts were used to generate that number. And all these things are important for measurement. So basically, one of the things that we're trying to devise and like promote with open source releases is this idea behind sharing metrics, evaluation workflows, and templates. And unfortunately, these are not going to be as easy as they used to be in the past. It is not just about like adding a metric. The concept of a metric, unfortunately, has become obsolete. There is no metric anymore. It is just like a script where you put together regular expressions, more, model calls, humans in the loop evaluation that end up producing a particular score. This is one example. This was work that was led by Tejas Gokhale, who is now a professor at the University of Maryland in Baltimore County. Basically, here we were trying to understand how good image generation models are in terms of understanding spatial relationships. Like if I say an elephant to the left of a motorbike, will it really do that? Like depict both objects and depict also the spatial relationship. And you have to take this in stages. First, you need to see, is there an elephant? Is there a motorbike, and are they really depicted in the right spatial relationship? So this is just like a very simple example of such a workflow. And then there is benchmark saturation. So many of the numbers that we see today in technical reports, they are reaching the mid-90s, if not the higher 90s. And it looks good. It looks good on paper. But then the thing is, like many of these things, we don't know if there has been memorization. Even if there is no memorization, even if this data has never been used in training data, the fact that it is saturated makes it very difficult to kind of measure progress and see where the gaps are, because it means that the benchmarks is perhaps too easy for this model. So one of the concepts that we are trying to push recently is dynamic benchmarks for generative tasks. I'll go very quickly on this, but basically, like what we're thinking about is having these benchmarks where you can generate other copies of it. GitHub is one of these. For instance, this is in the language space. You may ask the model, find a list of books that were written by Isabel Allende, who is the author, that satisfy a constraint, like having a single word in the title. And you can think about, like, you know, doing the same thing with other authors or having other constraints. And if we see, you know, like if we run measurements on this particular task where the user has very concrete, expectations from the model, we see that constraint satisfaction can be as low as 50%, which is like really, you know, like half of the cases. And again, in this case, even if this benchmark gets saturated, you can generate multiple copies of this moving on. So let me see. I will try to wrap up with a few things that maybe you can follow up later since we're at time. Another challenge in terms of like evaluation is scaling for interactive settings, as I was mentioning earlier. Sigma is a prototype that was developed at Microsoft Research. It's sort of like an application where you try to conduct a task in the physical world, and the AI assistant tells you like what to do. So I ran their user study. So this is work by my colleagues. And the task was to make coffee. And I asked the model, well, which of the capsules should I use? Like the blue one or the brown one? And the model was really nice, was like, well, use whatever you like, whatever you prefer. But the thing is, the blue one wouldn't fit in the machine. So physically, this is not possible. And the benchmarks that we are using today, where we ask like, what is on the table, is really so far away from the things where you know we want these models to go. And then finally, another topic that has been of a lot of interest for us is transparency around data and models. So there are many different forms of transparency on understanding like the impact of data in model accuracy, functional interpretability, where you try to understand like what is the impact of different input pieces into the output, and then more mechanistic interpretability, where you basically try to understand the impact of each of the components in the transformer architecture. There's like two works that I want to bring to your attention here. One of them is related to understanding the information flow in attention layers for constraint information retrieval. Like if you ask, is there a movie that was directed by a particular director that won a particular award? We see that if you really like visualize the flow of attention from the constraint to the generation, you can really debug which of the constraints was satisfied and what was not satisfied. So I suggest you like to look at the paper. We have a recent extension of this in the multimodal space, where you may have like visual constraints. For example, the prompt here may be, where is this place located in? And the constraint here is this place, like, this location. And we see that even in the multimodal space, it is possible to really track what MLP layers are responsible for transferring information from here to the generation. We see that the patterns here are a little bit different in vision from language. Things happen a lot earlier, and I suspect this is because of the, joint architecture. And it is also possible to edit knowledge in these models post hoc. And you should take this mostly as a causal experiment rather as an accuracy improvement experiment, meaning that it is possible to intervene in these models. So that said, in the interest of time, I will conclude. These are like some of the challenges that I hope we can talk about later. And thanks again to my collaborators, and the voice is back. Thanks.
For question answer. Thank you so much for your amazing talk. Any questions from the room first? Or from the Zoom? Like, I can ask a question. So you mentioned a lot about like, okay, so there are some tasks that you want to evaluate and we are missing the benchmarks for them. And you also mentioned that like there are so many capabilities that are being introduced that we don't know about them. So what's kind of like, what's your thought around like this unknown and evaluation or like prediction for things that can go wrong with these models? Because we have these base models and we have certain like benchmarks for assessing for certain tasks, but not actually like this capability of like predicting what can go wrong or like which type of tasks these models could be used for.
Yeah. Thanks, Nagar. So there's a couple of points here. Like one of them is in terms of like, how do you broaden up in terms of capabilities? One of the things that we are trying out right now is focus around like more fundamental capabilities rather than looking at like very application specific things, because there's many different types of evaluation that happen at like, pre-training time versus at the application time. And what I mean by fundamental is things like, if you want to see how good a model does in gaming, in navigation and things like that, any model needs to understand space. Any model needs to understand like what is north and south. So this is a very fundamental thing. And we're trying to see like, what are these proxy tasks that are really, at the basis or of any type of reasoning, and how indicative they are for downstream applications. Now, that said, like we're also just trying this out and like trying to see whether these things can tell us something. But this would be one way. And then on understanding what things can go wrong, there have been several tools that we have published in the past in terms of like error analysis and finding slices of data that have a lower accuracy. I think there's a lot of tooling out there. A lot of it though has to be adapted to the generative space, and allowing for a richer exploration that spans different modalities. I think this part of like moving from one modality to the other and being able to explore interactively is still missing from the tooling. Yeah.
Thank you. Thank you very much. We will go because of the time. Yeah. Thank you so much, Smira. So our next speaker is Miranda, your family name? Bogan. Talking about responsible generative AI from the ground up. Welcome.
Thanks for having me. So a few years ago, I was working at a tech company that I won't name, and we were trying to design a governance process to identify which models or systems required which types of due diligence or which processes, which mitigations, et cetera, either while, before they were being built or at a point when developers wanted to deploy them. And the team I was working with decided that we needed to ask sort of the minimal amount of questions to get the signals around which models needed to be routed to which content. I mean, we didn't decide that. That was the constraint we were given by the teams we were working with. And we decided that one of those questions that we needed to ask was, what is the domain in which this model or system is likely to operate? Because there's a lot of context around, is this model going to be used in a housing context? Is it going to be used to inform what jobs people get? Is it something geared for children? Each of those might have different legal requirements or different concerns that stakeholders had. And we wanted to have a signal of whether that was the intent of a model. Obviously, with generative AI, that breaks a little bit. But one question we wanted to add in that category was, is this a generative AI model or tool? And the answer we got was, nobody's going to know what that is. This was 2 years ago, and I think we all know a lot's changed since then.
Slides are not updating on Zoom.
So I think we know that a lot has changed since then, and my talk will be a little bit more of a provocation and a reflection on some of those existing problems that we've faced over the years in AI, and what that might mean moving forward for the responsible generative AI space. My slides are more of sort of like flags and signals rather than content, but we're trying to get this.
Oh, this one? No.
On the toolbar, it says resume. Each navigate over to the slide that you're trying to see. There you go.
Great. Cool.
Okay, thank you for pointing that out. So to give some context about where I'm coming from, I'm not an AI researcher. I've worked quite a bit with industry researchers, with academics, but after my time in industry, this was about a year ago, working with model developers, product teams, colleagues who worked on responsible AI, I decided to move back into the public interest space, which is where I'd come from before I was in industry, because the policy conversations, those kind of societal conversations around AI had just heated up so much over the decade that I've been working in this space. And we've gotten to a point in the AI policy conversation where we're moving from conceptual senses of, oh, we need transparency, we need explainability, fairness and representation, to questions of what does that actually mean in practice? What are the incentives and constraints and requirements that ought to be imposed to make sure that the right amount of attention is being paid to these issues so that they don't get deprioritized in the swirl of desire to kind of launch these new and exciting products. This is like an really important moment where the governance of this technology is emerging, and it felt like a really critical moment to bring some of the perspective from the practice community into that policy conversation to help guide what the requirements were going to shape up to be. So the initiative that I now lead is based at the Center for Democracy and Technology, which is an advocacy organization that's been around for about 30 years. It's been involved for those decades in really critical conversations around free expression and privacy and surveillance, and recently in AI. But even they recognize that these conversations around implementation of what does it take to do this work, what are the ways that assumptions about what good looks like could actually go wrong in practice, and what are assumptions about what it takes to do this actually need to be amplified. They knew they didn't quite have that depth, so we decided to launch an initiative called the AI Governance Lab, and our main goals are threefold. First is empowering practitioners to actually build AI responsibly, whether by helping illuminate what that means for people who are grappling with it, giving sort of a normative signal around what good ought to look like in very complex spaces, or helping to untangle and remove roadblocks to actually doing this work. We know sometimes there are legal constraints actually in a surprising way to moving forward. Sometimes there is ambiguity in how to move forward, and so you can't get the appropriate investment to actually move forward. So empowering practitioners to do the work well. The second is to create an ecosystem of accountability to make sure that organizations who say they're doing this work are actually doing it, and they're doing it to a sufficient degree. This is all very, still very nascent. There's not a lot of robust structures that actually can bring this work about and make sure that it's happening to the degree we need it to. So we're trying to encourage that. And then finally, it's helping policymakers and public interest groups and stakeholders understand the space, understand the conversations that are happening, sometimes at a technical level, sometimes at a policy level, so they can help with those first two things. And so I've been now back in the policy community for about a year. It's moving very quickly, similarly to the research itself. And really what stakeholders in that space talk about when they talk about responsible AI, accountable AI, et cetera, tend to focus on two pieces: the measurement, which we talked about in the last talk, and mitigation, although a lot more is focused on the measurement and the process, and they just assume that once we measure, we'll be able to mitigate, which is its own challenge. So let's talk about measurement. Obviously, how we define what we're measuring is going to determine whether we find the thing that we're looking for. But as we know, measuring AI systems is significantly more challenging than it appears, especially when the qualities of the AI systems that we're looking to measure are actually quite hard to define, let alone quantify. They tend to be very fluid, squishy subjects. Take, for example, fairness and representation. We talked about that earlier. So an AI system can distribute opportunities, it can rank content, it can generate content that can perpetuate harmful stereotypes. And each of these problems requires a very different conception of what it is we're measuring for, different benchmarks, data sets, methods, et cetera, and requires a different approach to even know whether the system is leading to this outcome that we might be worried about. And if you measure the wrong thing, you're not going to find the harms that you might anticipate. So in the social sciences, and this is the work I did with my colleague Amy Weinkoff, just even trying to conceptualize the issue we were seeing, these difficult to observe things are called constructs. And the process of translating constructs into measurements is called operationalization. And the challenge is the details of how we're moving from construct to operationalization in many of the measurements today is happening in, maybe not as robust a way as we hoped it would, and certainly is not necessarily being captured and documented and discussed and deliberated to make sure that we're actually measuring the thing that we intend to, and that the measurement is actually measuring the thing it's intended to measure. That's, the concept of validity in measurement. And I think we saw in the previous presentation, the mention of, prompt versions and things like that. There's a lot of room to go even in the measurements that we're performing now to make sure that we're capturing an indication of what's going on. And I want to shout out some researchers, Abigail Jacobs and Hannah Wallach, who, several years ago were raising this concern in the fact community, in the fairness community. And there's been a lot of work that's built on that to point out the measurement and mismeasurement of fairness and how what we're measuring has maybe led us down some paths in the technical work that maybe aren't serving the goals that we have. And so this is a really core challenge, not only in generative AI, but in AI and responsible AI in the first place. Now, there is a lot of good work going on in measurement. There's progress being made. The challenge is that policymakers are looking for trustworthy signals to say, what are standards that we can set at this point? What metrics can we impose to feel confident that the systems that we're building that are suddenly exploding into the world are not causing harms that we care about? And while I think many researchers are aware of the limitations of measurements they're doing, at least I hope so, maybe not as much as we would hope. And we know that these are just initial signals of the capabilities of models or where models can go wrong, and maybe directional indications of where more research is needed. Policymakers don't necessarily realize that, and they think that these are definitive measurements of specific harms and that they are providing sufficient coverage to the types of harms that policymakers are trying to prevent. And so, I think there's also a lot of urgency felt by practitioner communities to coalesce around a set of measurements that they can then point to say, look, we're following, some reasonable set of standards to check our systems before we deploy them into the world. And we don't see any, terribly major issues. And so, we put it out into the world because we need to learn a lot more about these systems. And that disconnect between the current situation of measurement and what people expect measurement to accomplish, I think is a huge challenge that the community is going to have to deal with. How do you convey the status of the research that you're doing with humility and point out the path ahead so that people don't kind of over-rotate and rely on measurements that won't actually tell us what we want to know. And of course, measurement's not an end to itself. Generally, it's useful for prioritizing continued work, for mitigations, and it's also a signal about whether mitigations that we're applying are effective. And so again, if we're not measuring the right things, that whole prioritization will be misled. We won't know if the mitigations that we're working on are accomplishing their goal, and we won't have moved forward in the responsibility kind of domain. And if we take mitigations that seem to work, but that we haven't fully thought through, we get externalities and sort of unexpected consequences that we're going to need to grapple with. And so how do we build signals of the harms we're looking for in a way that will lead us to mitigations that will be thoughtful and effective in actually addressing the complex issues that we're dealing with? And so a fundamental issue in general purpose AI and in generative AI is that while the folks building this technology tend to be looking for holistic and scalable solutions because that is aligned with the way the technology is being built, or there are constraints that are being imposed so that more robust and contextual analyses of harms are difficult to accomplish or are going to take a long time. The approaches that we actually need to address the harms that are manifesting require significantly more domain-related context than I think we're currently able to bring to bear in this field. So having alluded to the situation at Google, I want to talk about an analogy that I find helpful in explaining foundation models in generative AI to policymakers who aren't familiar with the concept, and that's the alphabet, lowercase alphabet. And I like the alphabet as a metaphor for this technology because it's has similar characteristics of the building blocks of something bigger, that once you understand the relationship between this foundational piece, you can then understand maybe how words are constructed, you can understand grammar, you can build in vocabulary, you can ultimately develop maybe coherent and even insightful thoughts. And teaching the structure of the alphabet certainly helps learners kind of move through those layers of abstraction up into sort of higher order tasks that they're able to accomplish. But teaching the structure and the frequency of letters in the alphabet alone won't reveal the historical context of what happens if you put the letter K together 3 times, or the risque connotation if you put the letter X together 3 times. Or the fact that if you hum, that maybe most people who went to elementary school, at least in America, will understand that you're referring to a particular part of the alphabet. Or that the letters C and D, or even B in certain families, can convey a sense of shame if the family, really cares about academic achievement. There are all of these contexts, there's all of this context around the alphabet that is unrelated to the structure of the artifact itself, that in order to understand the impact of engaging with this artifact, we really need to think about circles and circles outward from the artifact itself. And I think that's also the case with general purpose AI, generative AI. And so it's going to be important to figure out how to move within the generative AI context from this frothy excitement over how we put this exciting new technology into the world and leverage some of the really interesting things it can do, having built this sort of contextless, wide scale piece of technology into a market where it's going to encounter this context in a way that can be difficult to foresee. And even with, the best of intent in trying to spot some of these issues, new things are going to come up across different cultures that we're not familiar with, across different interactions of systems that lead to sort of complex externalities that are going to be difficult to develop accurate measures around, let alone even agree on what those harms look like potentially. And even more, I think these systems generally represent a compression of information in a way that collapses a lot of this context, and ends up leading to, you know, a small set of outputs, or even in certain cases, a single output that reflects some kind of, you know, sense of, this some sort of sense of what is the answer to some of these questions. Even the benchmarks are kind of framed around this idea of what is a right answer, what is a wrong answer, what is a harmful answer, what is maybe a beneficial or useful answer. And, you know, and express the sort of understanding of the world, this sort of foundational sense of reality. But if history tells us anything, it's that there isn't actually much of a universal truth, even in things where there appears to be so. So to kind of back up, you know, I'm not a technologist. I didn't study computer science. I play one on TV. But I got into tech policy in being really interested in the role that tech platforms play in the world, especially when they're taking on roles of entities that are more similar to nation states or empires. And a really defining piece of that was defining international borders in mapping products. And so, you know, I traced some of the decisions that companies made in trying to navigate this thing that might seem like it ought to be obvious. There are borders between countries. They've been decided at a certain point in time, and we can draw them on a map. Most maps throughout history have been static. And so initially, when Google started developing its Maps products, and people started raising questions that there might be an indication of a preference in taking sides in a historical or geopolitical dispute, the company tried to note that it based its maps on international standards, and they tried to point to sort of authoritative sources of information for where those borders sat. But when people were zooming in and out in these maps, there tended to be discrepancies between the products itself and some of those sources. And it turned out that there were some technical issues in the imprecision of how the borders were being rendered that were leading to actual confusion or perceptions that the company was actually kind of taking a side in some of these issues. Now, a couple of years later, there was a controversy in how Google Earth rendered this region at the border of India and China, Arunachal Pradesh, and in a way that indicated that the territory was within Chinese jurisdiction, which was actually against the law in India. Each of those countries had a law that actually required maps to not undermine the sort of national priorities of the country, such that it was actually impossible for the company to reconcile this and have one single source of truth. And ultimately, over time, the company determined that it could deploy localization and actually address this and actually show different maps to users accessing the site from different IP addresses and from different top-level domain names. And so it led to a circumstance where the company was showing these two different maps to different people, and then to everyone else in the world, it showed dotted lines on either side, indicating that it was a contested territory, and trying not to lead to controversy to the extent possible, while also still following the constraint of the laws in markets where it was operating or trying to operate. And then following that, they kind of moved their policy to say it's Google's standard practice to show all disputed regions around the world. And it's been Google's consistent and global policy to depict disputed regions per the claims made by the disputed or claiming nations on its global properties. And then it eventually adjusted its positions again to kind of take a contextual approach and take into account both the laws, the sort of existing geopolitical circumstances, the expectations of local communities, and really take this cross-functional approach and case-by-case approach to figure out how to render maps in these situations. And so I'm quite worried about what this looks like in the context of generative AI, both because of the move, in the technology to find, authoritative answers, or to at least figure out what are the lines beyond which, answers or responses or outputs from these models shouldn't cross because of some kind of harm, but also the instinct that this might lead to personalize outputs of these systems, to contextualize, but without true understanding of the context of the questions that are being asked. Because a lot of the attention to models, a lot of the measurements of models, and a lot of the mitigations are at this sort of universal scaled level that is very difficult to take into account this type of regional context or contextual signals that will determine if that particular output or system interaction or something leads to harms that we might worry about. Now, another thing that I'm quite worried about is thinking about not only the interaction of people with these models in their sort of raw form through chatbots or through image generators or multimodal experiences, but what happens when we integrate these technologies into real world circumstances, whether layering them into other technologies, whether putting them into more agentic systems that are operating independently and trying to take action, and especially in high critical domain contexts like law enforcement or the military, or cases that are determining people's economic opportunity. And this is not hypothetical, this is already happening. So take, for example, Axon is a provider of body-worn cameras to police officers all across the United States and the world. And they're already trying to integrate foundation models and generative AI into their software and hardware tools to help add more efficiency in sort of police work, which can make a lot of sense if you're trying to make sure that these folks can spend more time in the community, maybe building relationships, reduce violence, etc. But if a model for transcribing police body-worn cameras is fine-tuned just on existing police reports and existing body-worn camera footage, it turns out that most police departments allow officers to review their body-worn camera footage before writing reports, which means that ultimately the reports themselves reflect a very particular perspective of what happened in a given interaction. And there are a number of examples that show that if, when there was a different camera angle that was introduced into a body of evidence, that it showed a very different depiction of what happened in a given interaction. And maybe court cases that investigated those circumstances found that the depiction of the body-worn camera itself was very much from the perspective of the officer, as was the report. And if we don't include that context and an understanding of what might have led to the circumstances of that footage and that transcription, the models that we build on top of that data also won't include that context. So how do we think about not only the models themselves, but what is not included in the models? How do we think about layering in this really important contextual information into the technologies that we're building and that we're trying to test and mitigate harms within? Now, I think we all know there are a lot of issues within the models themselves, and we should do our best to try and figure out what can be mitigated at that foundation level. A number of examples here, but I think what's interesting about these examples that really keep me up at night is that while they share a lot of thematic characteristics, each of them required an understanding of the context of harm that they were looking at to develop a measurement that indicated whether that harm was happening. And so again, how do we kind of include that within our conception of what responsible AI includes? So my main sort of takeaway I hope people walk away from today is thinking about, we should think about what's different with generative AI. We should think about what novel approaches or sensitivities to the technical interventions that will be required to address the risks that generative AI poses. But we also shouldn't forget some of those unsolved problems that were spoken about earlier as well. Because I think that as generative AI gets layered into these other systems, especially again, these interactive systems, these agentic systems, we're actually going to reconverge from traditional machine learning and automated decision-making with generative AI and come back to some of the foundational problems that we haven't fully solved to begin with. And so I really hope people don't leave behind those issues and that your organizations don't deprioritize them either, because they will continue to be relevant and they'll continue to be latent in these systems if we don't think more more carefully about how to not just build scaled approaches to large scale systems, but think about what the context of the deployment of these systems look like and who needs to be involved in defining the problem and fixing the problem. Thank you.
Thank you so much. Thank you so much. So we have time for one question. And we apologize to speakers for like rushing things because of like our initial like technical difficulties. So does anyone have questions? Yeah, so louder, please.
Thanks for the great talk. My question is, policy making has traditionally always lagged behind pretty slowly, and this is a field that's moving at. How do you see that working playing out over the next 5 to 10 years?
Yeah, the way I'm thinking about it, and my project is thinking about it, is what are the building blocks, both of the technology, of the sort of responsibility efforts, and of the policies that we need to ensure that we can craft the right policies over time, because we probably won't know all of the issues that will arise, and we also don't know what interventions are going to be most effective now. But if we don't have some basics like good documentation of these systems, or good and knowledgeable institutions that can engage with the developers of these tools and ask the right questions, then we'll get to a point 10 years from now where that divide is even bigger. And so thinking about what pieces do we need now, what incentives need to change so that organizations developing this technology are investing in the right efforts, making sure that they're retaining the teams who are asking these good questions, and that they're not sort of preventing the learnings from these types of harms from being shared with other folks, so we can really craft the right policy solutions. Then we'll end up in 10 years in not a great place.
Thank you. So now I want to invite the speakers of the contributed talk, Gelda, a generative language annotation framework to reveal visual biases in image generators. Welcome. You're a little bit short in time, so
I'll do my best to go fast. All right, hey everyone, hope you're having a good CVPR. My name is Krish Kabra, and today I'll be presenting quickly GELDA, a generative language annotation framework to reveal visual biases in image generators. This is work done alongside Katie Lewis, as well as my advisor, Guha Balakrishnan. So suppose I'd like to use a text-to-image generation model like Stable Diffusion XL to generate photos of professors. So I can type in the prompt, a photo of a professor, and hit generate, and Stable Diffusion will generate images that may look like this. And now, while these images look visually quite realistic, many of you will notice a problematic pattern, which is that many of these images contain older male-looking faces. And as many of the audience members know all too well, for a long time, we know that image generation models exacerbate social biases. And in fact, an article by Nicoletti and Bass shows that when using Stable Diffusion to generate headshot photos of different occupations, the model exacerbates gender and racial biases when compared to US demographics. But even beyond social biases, we do notice some other patterns. For example, all of these professors are wearing eyeglasses. Another example is that all of these professors seem to be wearing some sort of formal attire, like a suit or a tie. And I don't know about you, but most of the faculty that I see on a day-to-day basis don't wear such formal attire, and they wear some questionable sweaters. And while these biases may not be deemed as less harmful than biases associated with protected attributes like age, race, and gender, they're still important to study and potentially mitigate against, especially when it comes to the responsible deployment of these models. But unfortunately, many of these types of biases remain hidden. That's because the current bias analysis pipeline requires us to use this predefined list of attributes to study for bias. And a predefined list is very prone to blind spots. And so attributes not considered by researchers will ultimately not be annotated and not be analyzed for bias. And trying to anticipate all the potential attributes for bias is inherently difficult to do so. What's more, using predefined lists is only useful for a particular domain. And in a world where text-to-image generation makes it very easy to create images from arbitrary domains, it's important that our bias analysis pipeline can also be extended to other domains. Is there an issue with the Zoom?
Yeah, Zoom is getting your speaker notes.
Oh, okay.
Wow.
Just desktop view. Is that better?
Yeah, looks right.
Okay. Apologize to the Zoom for seeing those speaker notes. So take, for example, these stable diffusion generations for a photo of a living room. We can see some biases with respect to style and color scheme. And in understanding these types of biases may be important for like an interior designer who's using this within their creative process. And it may unconsciously bias them towards making certain creative design choices. And we'd like to make sure that they're aware of these types of biases. So the question is, how can we create such a flexible method that can analyze bias across a variety of image domains? Our inspiration comes from the recent advancements in large language models. Given that these LLMs can capture a significant amount of world knowledge, we asked the question whether they can be used to generate attributes that can be useful for bias analysis. But we recognize two main challenges. One, how do we prompt the LLM to generate an exhaustive set of domain-specific attributes? And two, how do we choose the appropriate vision model to annotate each attribute? This last point is important because we'd like an automatic framework to assess biases, especially at scale. And so to solve the first challenge, we propose a hierarchical attribute generation strategy. To understand how it works, let me give you an example using those same living room photos. The caption will be a photo of a living room, and we'll first ask the LLM, what are N attribute categories that can be used to visually distinguish the images described by the caption? So an LLM like ChatGPT will generate style, color scheme, furniture, accessories. And then we'll ask the LLM for each of these categories, what are M different examples of the category that can be used to distinguish the images described by the caption? And so in the case of style, this may be Scandinavian, bohemian, industrial, color scheme, neutral, monochromatic, analogous, and so on and so forth. And we see that this strategy offers a pretty good coverage of relevant attributes for a photo of a living room. To solve the second challenge, we recognize that zero-shot annotation skills of VLMs are very powerful. And the key difficulty is actually determining which VLM to use for a given attribute, as some VLMs are better suited to annotate some attributes. For example, image text matching VLMs like Blip or Clip are useful for image level attributes like style and color scheme, like in the case of the living rooms, industrial, Scandinavian, bohemian. But when it comes to object-related attributes, open set object detectors like OWLv2 may be better suited. So for furniture, OWLv2 would be a better choice. And so to choose the appropriate VLM, we ask a third and final prompt, which is, are the attributes from a specific category examples of objects or items? Answer with a yes or no. And so in the case of style and color scheme, the answer would be a no. And this would correspond to image level, and we'd use an image text matching VLM. And when it comes to furniture and accessories, it'll answer yes, these are objects, and we'll use an open set object detector like OWLv2. And putting this all together, this is what our pipeline looks like that we call GELDA, for generative language-based dataset annotation. And let's see how GELDA performs at finding visual biases. As mentioned before, we saw those biases with respect to style and color scheme, and indeed, GELDA also points these biases out, claiming that a lot of these living rooms have a bohemian and Scandinavian style and have a neutral or monochromatic color scheme, and fewer have like a minimalist industrial style with more eclectic color schemes like triadic or complementary. And when it comes to open object level attributes, all of these living rooms contain coffee tables, lots of them with sofas and armchairs, but few with TV stands and bookshelves. And with respect to accessories, lots of them with area rugs and throw pillows, but fewer with wall art and decorative vases. And these set of results are part of a larger set of results in the paper that I recommend you look at and come swing by our poster. In conclusion, we propose an automatic framework that can be used to analyze visual biases of arbitrary image generations. This offers practitioners with a helpful tool to uncover previously unstudied biases in a cheap, low effort, and flexible manner. And for future work, we hope to use GELDA to understand differences in attribute biases at scale between image generation models like Stable Diffusion XL and ImageGen. I'm happy to take any questions, and please do come by our poster. Thanks.
Thank you for a great presentation. Any questions? Sure, go ahead.
So my question is, so you're using large language models to see the application for the bias feature generative adaptation models. So, but large language models themselves, they have bias. So how can I make sure that the bias in the large language model will not affect the adaptation process of the image?
It's a great question, and it's true that these large language models and the vision language models that we use inherent biases, but we found that our strategy of that hierarchical attribute generation strategy does get a good coverage of a lot of the attributes that we are intending to use, and you know, a lot of those biases, they're getting that good coverage. We hope to kind of mitigate it away from some of those biases. Yeah.
Thank you. So my second question is, have you ever tried to use some multimodal like that?
Right. So that's another great question. When we were initially working on this, ChatGPT 4V had just been released, and so we didn't do much experimentation with that. So we didn't do some specific use cases with multimodal large language models. That seems like a great next step. But I think our pipeline in general is quite general, and you can plug in different DLMs or different large language models, and really it's a framework that we're proposing.
Yeah, it's just, it's not responding for some reason.
Now we will be having the talk from on latent directions, a simple pathway to bias mitigation in generative AI. So for the rest of the contributor talk, let's actually keep the questions, keep the poster room more exciting.
Should I share my screen? But then remind you to log into the information because I use this like but I need the link for the Zoom. Yeah, because if you can give me the link, I can just join and share. Okay. Let me see. Just send her the link. Yeah. Okay. Oh, let's see the way out. I'm not sure what's happening. So, let's see. Oh, okay. This. Let me share the screen. Yeah. Here. It's the other way around. A bit, some problems. It's just sharing the other way around. So I'm not sure why. Hold.
I don't know what.
Let's try the view.
Yeah, view, maybe.
Here, and then if someone knows how to help.
Or technical person.
You probably want to stop sharing right now.
Okay, yep.
And then you probably want to go over to whatever your PowerPoint or slideshow thing is. And then get that set up. You know,
Yeah,
if you're gonna go to presentation mode, now's a good time to do that.
Yeah, that's the other way around.
Yeah, and so these are two different displays, right?
Oh yeah, so
you should be able to move
now.
the displays from one to the other.
Great, and now we can.
Zoom.
Okay, thank you.
Okay. That's what I see on Zoom, which is probably not what you want.
No, oh my God.
Main goals. The first one is to explain what embeddings represent. And we do this to understand the existing biases we currently have